I assume you can all, like I said, see my screen and hear my voice. If you can't hear my voice or if something goes wrong, please do post in the chat and I'll try and respond to that. But the talk today is called Building a Culture of Chaos. Now we're going to get to the building a culture part in just a sec. But this is a lovely introduction, just explain the talk, the chaos in the talk here is refers to chaos engineering. So let me ask a quick question. You can throw your answers in the chat if you don't mind. Who here has ever done chaos engineering? Has anyone taken part in chaos engineering and chaos experiments? So I don't see many messages streaming onto the chat right yet. I ask this question a lot, and often I see a few hands go up, but it's very rarely the whole room, right? This is something that's been around for a while, but it's not really what I would describe really as a mainstream technique. Something that everyone does, considers the baseline. So I think it's useful to explain the kind of history, the context of chaos engineering. What is chaos engineering? We had that poll just a few seconds ago. So the history of chaos engineering, like most stories in our industry, starts in the early 2010s at Netflix. And at this time, Netflix was involved in a move to the cloud. So they were moving from their own private data centers to public cloud, AWS specifically. And as part of this, they didn't want to just lift and shift. They didn't just want to sort of copy all of their old systems and code into the cloud. They wanted to re-architect, take this as an opportunity to make things better, to redesign their services, to break them up into smaller, more independently deployable chunks. This is what many of us today would call a mainframe to or a monolith to microservices transition. Maybe some of you were involved in that. Maybe you've been involved in those in the past. And Netflix realized something very important as they were doing this. They realized that while we sometimes associate this term microservices with resilience and scalability and all of those lovely things, you don't get them for free. This isn't like a magic wand that you wave and you get them. You've got to work for them. And if you don't put that effort in, you can actually make things worse. Because when they had that one big system, that one monolithic server, if that system goes down, if something fails there catastrophically, the whole business fails. But if they have hundreds or thousands of services and one of those services going down causes the others to go down, now you don't just have one point of failure, you have multiple, potentially even hundreds or thousands of points of failure. So you've got to be really careful with how you design and think about these systems. So when Netflix was approaching this, they put together what they call the Netflix engineering principles. Now, full disclosure, I've never worked at Netflix, but I've been told that they printed these out. They put them on every wall so every engineer could see them, and they have to remember this. And the first of these Netflix engineering principles was that no service should be a single point of failure. If one of their microservices, one of their services goes down, obviously that's bad, right? You don't generally want services to go down, but they do. That's a reality of life. When it goes down, maybe it takes down a little bit of functionality. Maybe you have some degradation of service for the user. That's okay, but it should not be a single point of failure. That was such a critical principle that their second Netflix engineering principle was to never, ever trust that they got the first principle right. Lovely set of principles, but they didn't just leave this as a principle which they kind of stuck up on the wall. They actually built a tool to do this. And if you've heard about chaos engineering, you've probably heard about Chaos Monkey. So Chaos Monkey was a tool built by Netflix. And what it was a little automated tool During office hours, they would only ever do this during office hours when, Netflix engineers were actually in the office and able to react. They would turn on Chaos Monkey, and it would start picking random services and just start turning them off, simulating a failure. And if they got that first principle right, if they actually did build a system without any single points of failure, the system should keep working. The system should be okay. So they were essentially constantly validating that they had built a system without single points of failure by simulating those failures and seeing what happened. And they didn't stop with Chaos Monkey. They built a whole bunch of monkey-themed tools. They built Chaos Gorilla and Chaos Kong. These are sort of Chaos Monkey's big brothers. Chaos Gorilla simulates the failure of an entire data center, and Chaos Kong simulates the failure of an entire availability zone. So we're essentially testing the hypothesis here that, if a meteor wipes out the east coast of the United States, can we still watch Netflix? Which is an important thing to test. They didn't run these quite as often as Chaos Monkey. They didn't run these every single day. But again, it was still about validating that their system was able to recover from these failures. Not all of the monkey-themed tools that they built were quite so destructive. And one of my favorite Netflix tools is actually Latency Monkey. What Latency Monkey does is it inserts random delays, random increases in latency into network requests. So a network request that used to take 200 milliseconds, now it takes 2,000 milliseconds or 20,000 milliseconds. Have you set your timeouts correctly? Have you set your failover and your retries correctly? Because those are subtle failures. I'm sure they're things that we've all seen, and they can bring down systems. So Netflix built this whole suite of monkey-themed tools they call the Simian Army. And to their credit, they did a really good job of actually publishing these and making these available open source. Just for some context here, this is from a previous era where internet-based monkeys were fun and interesting and not just scams. But this played a really big role in popularizing what we now think of as chaos engineering. And Netflix kind of realized after the fact that they had invented something here. They had invented chaos engineering. They actually went and put together a site, a very helpful site here you can jump to, the principlesofchaos.org. And they describe chaos engineering, and they say that chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. I really like this definition. There's a couple of parts here, right? So they point out here that it's a discipline. Right? It's not just randomly turning off servers. People who talk about chaos engineering, including myself, are very guilty of just saying, hey, chaos engineering is about randomly turning off servers. It's not. There is a discipline to it, and we're going to talk a lot more about that later. I also like that it points out that it's experimenting, right? These are experiments. We sometimes call these chaos experiments. I'm going to try turning off this server. I hypothesize this is going to happen. I want to validate that hypothesis. That's an experiment. And it also talks about building our confidence in the system's ability to withstand turbulent conditions in production. This is something I think is really important as well, because here's the thing, systems fail. No matter how perfect our code is, things will go wrong. Even if our code is absolutely perfect, completely bug-free, sometimes the underlying hardware fails. The reality of building modern distributed systems, need any systems, is failure is inevitable. We need to be able to withstand that. I like chaos engineering because I think of it sometimes as an honest approach to engineering. It's not about lying to ourselves and saying, hey, if we just do things perfectly enough, everything will be cool. No. It's saying, no, things will fail. We need to make sure we're ready for it. The way I like to visualize chaos engineering is as kind of a loop here, right? At the top, we've got our chaos experiments, right? We run experiments. This is where we release the chaos monkey. And we try and break things. And when things break, when we experience those failures, we try and learn from those failures. We take these as learning opportunities. That failed. Why did it fail? How can we make this better? There's been excellent writing here. I know this is a very small image here, but I'll share the references at the end. Don't worry about that. It's the Etsy Debriefing Facilitation Guide, which is an excellent book by John Allspore and a few folks at Etsy. But there's been fantastic work done by people like them, Sidney Decker, Todd Conklin, looking at how do we really learn from our failures. And once we've learned from our failures, we improve the system's resilience. This isn't about preventing the failure. It's about making sure our system is resilient to the failure, about making sure it's able to continue in spite of that failure. Some people would call this kind of fixing bugs. I don't necessarily agree with that, but that's really more of a pedantic point on my side. And this is a loop. This is the key point here. This is something we do daily. This is something we do all the time. We are constantly validating our hypothesis that we've built a system without single points of failure. Now, this is all cool, but I have a little bit of an admission here. This is a little bit of a bait and switch of a talk. While I do want to talk about chaos engineering, my favorite topic and the thing I really want to talk about today is complex systems. So another question for the audience here, please do. I think you can use the Zoom reactions. I'm not sure which of these features Zoom has enabled here, but who here would say that you work in a complex system? Put your answers in the chat or give a little thumbs up. There you go. I see a couple of hands going up already. It's at least one hand going up. It's good. One person. I can't see who. Oh, I can. Wonderful. Anyway, one person has said that they, 1 to 2 people, so the number's sort of flickering on my other screen over there, technical challenges of not being in person, but there we go. So there's a couple of people saying that they work in complex systems. Now, the interesting thing here is I haven't actually defined what a complex system is yet. People were quite quick to put their hands up, which is bold. I like that. Taking risks there. And I like this topic of complex systems. I like to talk about and explore what do we really mean by complex systems. One of the properties of complex systems that we see is that they have what's known as multiplicity. Multiplicity just means there's lots of stuff in them, lots of elements, lots of agents, lots of moving parts. Maybe you've heard this phrase, right? Lots of moving parts. Maybe that's a little bit of a hint that maybe this is complex. But this isn't enough. The philosopher Paul Cilliers frames it as, well, if you go walking on a beach, there's lots of sand under your feet, right? There's lots of elements there. There's a high degree of multiplicity, but that's probably not what we think of when we say complex systems. Is sand really a complex system? Maybe not. We also need interdependence. We need connectivity between the elements in those systems. They are communicating with each other. They're talking with each other. They're passing information to each other. These connections are far more important than the elements themselves. Think about a crowd of people as well. You don't just talk to the same person. You talk to different people. You have different conversations with different people. These connections are dynamic. They're ever changing. They're also non-linear. What that means is a small input can result in a very large output. If I walk into a large crowd and I whisper to someone, fire, or I yell to someone, fire, that's a small input, but it might lead to a huge crowd of people rushing out of the building. So non-linear connections there. And there's also a high degree of diversity. So in all of these elements, while they're often talking to each other, often communicating, there's loops and dynamic non-linear interactions, they're not all the same. Which means their connections aren't the same either. The conversations you have with your colleagues are probably very different to the conversations you have with your friends. Different types of connections here. This is very important. So tell me, does this look familiar to anyone? Does this architecture diagram look familiar to you? See, We often see diagrams like this. Maybe some of you have drawn big architecture diagrams like this on a wall or a mural somewhere. I think it's because we see diagrams like this. We see all these connections, all of these elements, all of these moving parts. We see something. We feel that there's something there. That's maybe complexity. And this is a good start, but again, it's not enough. We also need to be thinking about the behavior and how these systems work and act. One very important property of complex systems is that observers change the system. Now, if any of you have stage fright, you will be very familiar with this. It's pretty easy to practice talking in front of a mirror in your bathroom, but as soon as you get in front of the crowd, that's very different because the observers change the system. The observers actually become part of the system, and the system changes because of it. I'm quite lucky. I don't get stage fright, but I do. I was pairing with someone a few days ago, and I failed. I mistyped my own name 5 times in a row. So that's, again, observers changing the system. This also has very interesting implications for people like myself who are consultants. I can never just go in and be this neutral observer. I change the system just by being there. And because every time someone interacts with a system, even as an observer, supposedly an observer, it changes, that means the systems adapt. We sometimes call this field of research complex adaptive systems theory. It's complex systems that adapt. Systems change over time, right? That's not terribly complicated. That's fairly understandable. I mean, systems change. Stop me if I'm going too fast. But this has very, very important implications for how we interact with them. Because it means that a plan that worked yesterday might not work today. Think back to March 2020, the first round of COVID lockdown, start of the pandemic, right? I actually spent most of that time in Germany, here in Berlin, where I live. And we had some pretty hard lockdowns. Loads and loads of people, loads and loads of shops shut. The world looked completely different to us. We had never seen this level of lockdown, this level of stoppage. I'm sure that's probably a somewhat familiar experience for many of you here. But the interesting thing is we kind of pulled through. There was this sense that, yeah, this is difficult. And we really don't like this. But we're in this together. Yeah, this is a tough situation, but we're going to pull through. The offer not valid for the British Conservative Party, of course, but there was a way forward there, right? We pulled through that. Now, let me ask you a question. If your government or the German government or wherever you are right now was to implement the exact same lockdown rules from March 2020, but they were to implement them tomorrow, would the reaction be the same? I'm guessing probably not. Because systems change every time we interact with them. Our plan from yesterday might not work today. We need to co-evolve with our systems, because if we don't, we will get left behind. Very important point. It's what's known as path dependence. We're dependent on the path we took to get there. And another important property is when we're thinking about these complex systems, lots of moving parts and dynamic interactions and nonlinear communication, we have unintended consequences. No matter what happens, no matter how carefully we plan and plot and prepare and design, we are always going to miss something. The image on the screen here, if it seems familiar to you, it's because it's one of the most widely circulated images in human history. It's what's known as the blue marble. It was taken by the crew of Apollo 17 as they left Earth on the way to the moon. A little fun fact about sort of missions to the moon is everything is timed down to the second, right? There's time to take a picture of this and take a picture of that and do that experiment. But this picture was unplanned. The crew had a little bit of spare time. They floated over to the window and they snapped this picture of the Earth hanging in space. And a little while later, there was a public campaign to publish these pictures, to get these live and in the public domain. And they succeeded. And for the first time in human history, the whole Earth was able to look down and see the whole Earth. Not see borders, not see peoples and cities, but see the world. The world is one, hanging in the darkness of space. This image is credited with shaping the environmental movement as we know it today, giving us a different perspective on the world. That was not an intended consequence of taking this picture. That was not something that they could have planned ahead of time. And if we were to go back in time and do it again, there's no guarantee we would get the same thing. As Barry Commoner puts it, the first law of ecology is you never just change one thing. The system is always changing. There are always unintended consequences. The system is adapting, as the Greek philosopher Heraclitus put it. You can't step in the same river twice. So when we're working with complex systems, there's lots we need to take into account. And there's many, many more properties and behaviors of complex systems that are well worth talks all on their own. But one thing is really, really clear here, and that is that we need new approaches when we're dealing with complex systems. And we are dealing with complex systems. We're working with teams and businesses, and no matter how carefully we scope our problem, there's always a wider, bigger, complex complex system that we're a part of. We need new approaches for that. And I see these approaches in some places. Maybe you've heard of big modeling upfront, or sometimes called big design upfront, or big requirements upfront. This is often talked about in the sort of agile community, in particular in the extreme programming community. Big shout out to extreme programming there. And when it's talked about, this idea here is before you start building something, before you start working, you spend lots and lots of time on planning, on modeling and designing and requirements. You do all of your planning up front so you know what you need to do and you can follow your plan. This idea is usually framed as an anti-pattern. And what we're doing here is we're acknowledging that no matter how carefully we plan, we're going to get things wrong. The system will change. So this is an approach that is relevant and coherent with complex systems. Maybe you've read the Agile Manifesto, right? One of my favorite manifestos. There's a line in here about responding to change over following a plan. Same point again. Yeah, we should have a plan, but it is going to change because, again, complex systems adapt. We build something, we put it in front of our user. The fact we put something in front of them means they now want something new. Nobody knew they wanted an iPhone until the iPhone existed. So yes, we should have a plan, but more important that we respond to that change. And there's nothing in the Agile Software Manifesto that references complex systems. It's kind of implicit. Some things do reference them very, very explicitly. This is Edge. This is a book I quite like. Full disclosure, this was written by 3 of my colleagues at ThoughtWorks. I'm not getting paid anything extra to promote this. I do genuinely think it's a good book. It's about how to run and organize a business in a complex system. And it actually is very explicit about this. It says the title Edge comes from the concept of the edge of chaos in complex adaptive systems theory. And it says, again, talking about planning, in times of uncertainty in complex systems, our traditional reliance on planning won't work. It's not that we don't plan, we do. We just don't believe our plans will survive reality. Again, this is good, relevant advice here. And there's other stuff. This is a whole book about how to run a business and an organization in a complex environment. But you don't need to read a whole book. I think you should. It's a good book. But there are simple ideas like we accept failure. Maybe you've heard someone say this In this team, this organization, this department, we accept failure. We embrace failure. We learn from failure, right? This is actually referenced as a property of high-performing organizations. You might have found that research in the Dora in the Accelerate book. We accept failure. I've heard this so many times. I've even seen it literally printed out and put on a wall. I walked into an office once and I saw this. We accept failure. I had a conversation with someone once about just some changes to their team that we were kind of suggesting, like, hey, let's maybe change how we work on this particular problem. And at the end of it, they said something really interesting to me. They said, fantastic. Like, I agree with everything you just said. But how do we actually make that happen? How do we actually change culture? Right? It's very easy to print something out and put it on a wall and say, we accept failure. But that's just a sign on a wall. That doesn't mean anything. Our culture is not what we put on the wall. How do we change culture? That was a really good question that I liked. And this is a very difficult problem. In fact, it's a complex problem because culture is a complex system. But there is an answer I like here. And it's from this guy. This is, for those of you who don't know, this is Aristotle. Aristotle was talking about what it means to be a good person. And he said, we are what we repeatedly do. Excellence, then, is not an act, but a habit. And again, full disclosure, technically, Aristotle didn't say that. That's a later philosopher, Will Durant, who's paraphrasing him. Important to quote your sources. We are what we repeatedly do. I like this, okay? Our culture is not what we put on the wall. It's not the sign that we say, this is our culture, here are our 5 values. Our culture is what we do. So this actually has a really good insight for us. It's not, the question here isn't how do we get people to accept failure? How do we change culture? The question is, how do we make accepting failure part of our culture? How do we make it a habit, something we do every day? And that's kind of where chaos engineering comes in. Because that's what it does. It makes learning from failure a part of our everyday work. It makes it a habit, forces us to do it and think about it every single day. There's another fun little principle here, right? An easy little sign you can put up, right? No plan survives first contact with the enemy. Although I prefer Mike Tyson's formulation of this quote, which is that everyone has a plan until they get punched in the mouth. The idea here is really simple. Your plan is going to need to change. As soon as you start acting, the system around you will change. You need to update your plan. Again, that core idea of adapting to change, accepting the realities of working with a complex system. And this is a lovely sign. You can buy this on Etsy for like 20 euro if you want. Maybe it'll change your culture. I don't know. How do you make understanding this, really embracing this, a part of your everyday work? And again, it's here. It's step 2. Step 2 is never trusting that your plan worked, is never trusting you got things right. It's constantly validating your assumptions. So we've got this loop here, right? And whenever you Google chaos engineering, you find a lot about this, chaos, about the chaos experiments, right? And one, I think, really important thing to emphasize, I kind of referenced this a little bit earlier, is that chaos engineering and chaos experiments isn't about randomly shutting off servers. It isn't about randomly, I'm going to destroy that service. It's a disciplined approach. We need to think about how we design these experiments. we need to think carefully about what we're actually targeting, what we're going to try to break, and what we're going to try and bring down. If we pick a service that we know is a single point of failure, and we run a chaos experiment on it, and it brings down the entire service just like we knew it would, we didn't actually learn anything new. We need to think about how we maximize our learning from our experiments. We also need to think about how we limit the blast radius. Netflix is a fairly mature company in this context. Start off with just a few services. Just take out one service here, one service there. Don't test on your entire business. If you take down your entire business, you might have learned a lot, but you are not going to be running any more chaos experiments. And you also need monitoring in place. You need to be able to know what happened. Okay, we pulled the plug on this server. What happened? Let's understand this. Again, this monitoring allows us to maximize our learning here, and it also allows us to react. It also allows us to roll things back when things get bad, when things go in a bad direction. There's a lot of discipline that goes into chaos engineering. And I found this really interesting because a couple of years ago, I was reading this article by Dave Snowden, 7 Principles of Intervention in a Complex System. And he talked about how you design experiments for a complex system. He said, one of the first things you need to do is you need to test the coherence of your experiment. Is this really a coherent hypothesis? We don't just want to test any random thing that comes to our head. We want to test the things that are going to lead us to learning. We also need to make sure our experiments are safe to fail, because some of them will fail. We want some of our experiments to fail because that's where we get the most learning. We need to make sure they are safe to fail. We also need to make sure we have monitoring in place so we know what's going on, how our system is reacting to our experiments. If you just break something and walk away, that's not an experiment. That's just you annoying someone. And we also need to make sure we have a damping strategy in place. If this goes wrong, how do we limit the damage? How do we tone down that experiment and the damage it's doing? So if you look at these 2 lists here of how we approach experiments, both complex system experiments and chaos experiments, we need to think about what we're actually targeting, not just running any old idea, but actually think carefully about what we're targeting. We need to think about how we limit the damage that we do. We need to think about how we have monitoring in place so we know what's going on and how the system is responding to our inputs. We also need to think about how we limit the damage when things do go wrong. Now, if you're looking at these 2 lists and you're thinking, why, Steve, these are the same list. Yes, congratulations. You figured out the point of the talk, which is that a lot of the skills that you need to work with complex systems are some of the same skills that we build up when we work with chaos engineering. We are embracing the inherent uncertainty and the complexity and the failures in our system. We're approaching these systems in the same way. I don't want to tell you that chaos engineering will allow you to surf through complexity and deal with all of these difficult, complex problems perfectly. But I do think it's a pretty good first step. See, there's more stuff that goes into working with complex systems, stuff we don't have time to talk about today, unfortunately. But when we talk about chaos engineering, there's a big focus on the experiments, how to break things, how we learn from failure, how we improve the resilience of the system. These are all important, big topics, but these are also first, and in particular, improving system resilience. That's a great goal, right? We do chaos engineering to make our system more resilient to failures. That's a very, very important goal, a really valuable thing that we can get out of these experiments. But it's also a first order effect. We do chaos engineering in order to improve the system resilience. What I've been talking about today are the second order effects of chaos engineering. How does it impact the system as a whole? How does it impact our culture? How does it change how we think about our work and our roles? That, I think, is much, much more important and much, much more valuable. And for that matter, think about some of the other techniques that we use in our day-to-day work. Think about continuous integration or continuous delivery or test-driven development. We know what the first order effects of those things are. We do test-driven development, so we have more test coverage. Cool, that's a good first order effect. But what are the second order effects there? How does it change how we think about the system? How does it change our culture? Unfortunately, I'm looking at my time and I am out of time. So I will leave that little question as an exercise to the audience. I will say thank you very much. I've been Steve. I'm a QA consultant at ThoughtWorks. We're a global technology consultancy. So come say hi if you ever want to work with some lovely, clever people. References for this talk are all here. That is it. That's the end. You can follow me on Twitter for the remainder of Twitter if you are so inclined.